for a brief postdoc, and then we moved to Trieste as first as a postdoctoral fellow at CISA, and then as a Ludwig Boltzmann fellow here at ITP. And since 2022,
last year, yeah.
Since last year,
September.
he's an assistant professor at University of Trieste, where he teaches at the Artificial Intelligence degree program. But he also teaches at CISA and here at ITP. And today he's going to give this quite introductory talk to machine learning, which is his main research topic, and they mostly focus on unsupervised machine learning. Without further ado, Alex, the floor is yours.
Okay, hello to everybody. So, for me, I'm really happy to be invited by the University of Trieste now that I'm here. So maybe I can start meeting people from physics. Now, by bureaucratic questions, I'm under mathematics, but I'm inside, let's say, for chemist, but work in physics. Okay, so when Valerio and Antimo suggested me to give this seminar, I was thinking what to explain you, because unfortunately the people that are sitting here in the knowledge of machine learning techniques. So my idea was, okay, let's try to rise the level of those that don't know anything. Okay, so we will try to start from the very, very beginning. And at the beginning, before doing any seminar, I like to start like that, saying what I'm going to explain. So if you want to leave that, feel free. Okay, I will start just introducing to you what's machine learning, or at least what's my definition of machine learning. And then we will try to classify things in such a way that we understand a bit more what we are talking about when we are talking about machine learning, and then see some basic concepts that I explain to my students at the University of Trieste that are at the basis of what's machine learning. I mean, what I told them is that they are people from AIDA, intelligence and analytics. And I tell them that without these concepts, if they find something of that in the exam, they're not going to pass. Okay, because that's at the basis. So once we have seen this, I will start with some selected applications in the field of physics. Okay, and we will see. I have put 4 of them. I don't know if we are going to have time to see the 4th one. I put them in order of lower order of my implication on the project. So the last 2 are those that I have already done, let's say. So if we don't have time, you have always time to ask me. The other ones, I can explain them. Okay? So let's start. Oh, okay, before. Please don't interrupt me. We are in a seminar, but it's kind of friendly. So do not hesitate to interrupt me, questions, whatever is not clear, ask. Okay? So I don't know if there is a way not to.
Yeah.
To do it somewhat. It should disappear, but it's not doing that. So. Yeah. Okay. Okay. Perfect. Thank you. So yes, there are also places. So this is a slide from Dune. I don't know. For those that has a nerd soul like me, would be already known. And the thing is that they say you shouldn't do a machine that thinks like a man. But what I want to say before is that we have to lower a bit our expectations. We are really far from it. Okay. So let's lower a bit our expectations. And what happens many times in machine learning is that you teach one identification, and then the machine starts identifying the same in different ways, right? So we are, let's say that the state of the art now is much more near this than the previous one. We are extremely far of doing something that thinks like this. Okay? This is something that is not strictly true, but it's really related. Let's say that you start from statistics, then you put some kind of nicer thing and say that's machine learning. And then when you call it artificial intelligence, we should go to the bidding room instead of here. Okay, it's not exactly like that. Let me put some, maybe, let's say, machine learning has a strong basic on statistics, but has some specificities that make it different from that. Okay, so we need to learn statistics in order to understand machine learning properly. But let's say that we move in slightly highly overlapping spaces. That's slightly different. Okay. So this is what I would define as machine learning. Machine learning, it's a set of algorithms that infer information from the data and in an implicit way. Let's see what's that. Algorithms. And since the name says we need computers. We need computers, and computers work through algorithms, right? So the idea is that we don't care too much about which computer. That's work for people from informatics. Okay. When they want to optimize the algorithm, all that stuff, that's their work. What we care is about something that makes sense in order that the computer learn. What's infer information? Learning is the same. And this information can take many forms depending on the problem that we are going to solve. Okay? So when we will see examples in which this information has different ways. But at the end, both are information that we want to retrieve with machine learning. And we learn them from data. Let's say that all the things, all the algorithms that make machine learning different from other ways of learning is that we are absolutely focused on the data. The data teach us how to do the things. We try to minimize our input. We try to minimize the knowledge, the know-how that we put in the algorithms. We try just the machine to learn this know-how from the data that we provide. And it's an implicit way. It's an implicit way because we don't learn, we are not reading books in the sense that, okay, if I imagine in an image recognition algorithm, if all my images had a label written leopard, it would be too easy not to recognize. I want my machine from the features of my data learn what we are doing. Okay. So let's go for the classification. And there are many ways of classifying machine learning algorithms. Depends on what book you read. I like this one. And the first kind of hierarchies. It makes a first hierarchy between data-driven algorithms and what is called on-fly algorithms. We see both of them. And then within data-driven, there is a difference, an important difference between supervised and unsupervised machines. Okay? So let's focus on the upper part of the tree and data-driven. Data-driven is associated with a hard disk. And the idea is that we need a lot of data. Okay, so we're using that. What we understand by supervised learning. In supervised learning, what we have is a set of data that it has some features. Its data point has its features. That is this X, right? This X would be our data. And it's associated with a ground truth, some kind of label. This label could be a pure label, a class, say, or it can be also a output function, can be a real number, okay? A bit different, but the idea is the same. And the question is that we have that, and from that, we try to learn a model that allows us to predict new outputs, new Y values for unseen data, right? We have a lot of data, we learn from this data, and then what we expect is to have a function that correlates the input, the X, with the Y. And the idea is that what we learn are the weights that module our model. We will see one example later explaining that, but you can imagine that if you are doing a linear regression, that all of you have done before, what you learn from the data are the coefficients of your linear regression, right? And then you expect that this line that you have learned from the data can be applied to other values of X, right? The idea is that indeed, we will see linear regression can be considered part of the machine learning algorithm. So, unsupervised learning is a bit different. And what we try to learn are the features of our data itself, without any label. Okay? We just try to learn things from how our data is distributed. Okay? Let's see it in a way that probably it's more familiar to you. Let's see it from probabilities. When what we do in supervised learning is to learn conditional probabilities. We learn the probability of having a given answer, a given Y, given all the features that we have from the data. And that's what we learn. In supervised learning, we learn directly the probability distribution function from our data. That would be very nice to have that. Many times we have to just learn some properties of this probability distribution function instead of directly the probability. Okay? So let me do some simplest algorithms. Okay? The simplest one that you can imagine is the linear regression or polynomial regression, whatever form you want to say that. There are three places. If you want, exactly three. So you can get. So in linear regression, the task that we are performing, it's called regression. And it's called regression because the label that we have, it's a real number. It would be equivalent if you have a vector of real numbers. But if you have a real number as output to your function that you're learning, what you're trying to do is a regression. Then there is another called regression, but it's not a real regression, that is the logistic regression. I don't know if some of you have already seen that. Anyway, it's a really easy classification algorithm, and what it performs is a different task. The task is classification. It means that I have a ground truth with classes of all my data, and what I want to predict in the future is the classes given the features. That's what we learn when we try to do image learning. You see that that's one of the most successful fields of machine learning now, image recognition. What you want to do is that if I gave you one of my photos in Facebook, you recognize my friends. You are not giving me a number You are giving me directly the name of that campus, right? That's what you do, it's classification. Then another task that maybe many of you already have performed is to do what is called dimensionality reduction. So we as physicists, let me call it physicists, even if I'm kidding, usually deal with high dimensional data, really high dimensional. And if we need to visualize it, we need to project it. If we are really, really good at visualization in 4 dimensions, because we can add the time to the visualization, but no more than 4. We cannot visualize anything that is in more than 2, 3, 4 dimensions if we add time to our visualization, right? So one technique that we can learn is how to project our data from really, really high dimensions to a lower dimensional space. And we will try to do it without losing the information that is in our data. Because the easier one would be, okay, I cut all my features to just 4, 3, whatever. But then what I risk is to lose a lot of information, right? What I try to do in dimensionality reduction test is to move from a high dimensional space to a lower dimensional space without losing information. For many of you that work, for instance, in condensed matter, that's something that we do every day. When you go from configurations in the space to the order parameter, you are doing a dimensionality reduction, an extreme dimensionality reduction, right? Because you are going from all the degrees of freedom of your atomic system to 1 parameter, right? So that's the same, but do it without knowing anything. The difference is that I let my data to perform the dimensionality reduction.
This is when you want to find descriptors of your.
For instance, you can use it for finding descriptors. Then another task that many of you have done, sure, it's a histogram. A histogram is nothing else than learning the probability distribution of your data, right? So it's something that you don't need labels. You are learning how your data is distributed. So it's another task that you can do with machine learning. Another task is to understand if your data is just one group or there are many groups. That's what it's called clustering. Okay. And if you want, I will share the slides. Okay. All these tasks that I told you can be classified in these 2 big groups that I already told you. The 2 first are supervised learning, because you need a ground truth in order to do them. The other 3 are unsupervised, because here I just use the properties of my data. What K means? K means it's the name of the algorithm, the clustering algorithm. It's probably the easier and the first clustering algorithm. Okay, I just try to put the simplest algorithms for doing each of these tasks. Okay? In any way, even I have to say, I work in clustering a lot. There are a lot of algorithms on clustering, but even today, if you look for clustering, the citations of k-means are increasing exponentially. They have hundreds of thousands of citations in the paper.
Can I ask, so in the classification, you have a basic criteria,
yeah,
and the data gets classified based on that.
You know how to classify your data.
But is in the clustering, this
emerges from the data. Yeah, but you don't know how to.
It's not.
Yes, but you don't know what's the meaning of these groups. You know that they are putting groups, but you don't know if you are putting cats with dogs or you are classifying other kind of things. You are just learning if there are groups in your data or not. Okay? One thing that is basic in supervised learning and also in other techniques it's what it's called loss. Because for learning, the computer needs to quantify how well or how bad he's performing and trying to optimize that. The classical way is trying to minimizing this loss, minimizing the errors. That in the case of linear regression, it's trivial, right? We have the quadratic error. In the case of logistic regression, it's not so trivial. You need to quantify how somehow. Well, one way that you can do is just count how many ways you make a mistake, but that's hard to optimize. So you have to obtain a loss that can be minimized and that stuff. So in this case, I put here the cross entropy, but there are several ways. I just want you to realize that there is always this concept of loss that you are trying to optimize when you do machine learning. Then let's pass to what we call on-fly machine learning. And on-fly machine learning is called on-fly because imagine that you are teaching a boy to children to walk. You are not providing the children with a lot of examples of this. It means fall, this means fall, this means fall, this means that you continue, right? The children will learn by itself by trial and error. Yes, sorry. And unsupervised, it's hard. Not all the methods have loss. PCA, for instance, in dimensionality reduction, you can think about using losses because you somehow can quantify how well your projected data recovers the information on the high dimensional data. On clustering, for instance, it's really hard to obtain a loss. In K-means, you have a clustering, you decide a clustering, but it's not always, it's not so uniform as in the case of supervised machine learning. So, as I was talking, on-fly, it's a different way of learning. You are not learning with examples and counterexamples. You are neither learning from the data, you are just learning from trial and error. Okay? And this trial and error, it's called what is called reinforcement learning. Imagine that you have your robot that has to decide where to move. What you have to do is to define a policy that gives a reward when it does it properly and a penalty when it does not properly. Okay? And then you let the system evolve. And by doing many trials and errors, you will expect that your robot learn to avoid the fire, right? This, but it's a really easy thing, have led to a really complex and really successful results. For instance, I don't know if you have listened about AlphaGo. Okay, that's Google had defined a machine that had learned to play Go and had beaten the world champions in Go. That's something that has not done before with standard computers. But even the good part of this machine is that if you, instead of teaching the same machine, the same algorithm to play Go, you teach it to play chess, it does it. And it does it also at really, really high level. Okay, so it's a different paradigm. You see, with Deep Blue, we had for the first time a computer that was able to beat but the way it was done, it was just exploring a lot of computing, no? Computing a lot of possibilities. This is done in a different way. The computer learns by itself, just you put the rules of chess. That's the thing. So what happened in the case of Go is that they discover new kind of movements in Go that no one was taught before. Because by playing, of course, it was a huge computational work. Because you have to imagine this computer playing Go against himself many times in order to learn the rules. Not the rules, to learn the best way of moving. But with this way, it performed a really successful task. Okay? I have to say that this is not my field of expertise, so I would not talk anymore about that. If you are interested, we can talk to other people in the department. Yeah? But one thing that we need is data. And let me put it 3 times. And for the data, for us, that we do simulations, we obtain it from supercomputers usually, right? This is, for those that work on molecular dynamics, this is a photo phantom that provides extremely long molecular dynamics simulations. Okay? And the question is that what I told you before is that we have a set of features and a response function. Huh? But the question is that the data is usually more complex than this set of features. Imagine that we want to classify images, how to transform these images in a set of features. It's not trivial. For instance, yes, you can do this, put each pixel as a number in a vector. But what happens if I have images of different size? I have to decide. What happens if I have many colors? I have to add more features. So it's not like I have a 2-dimensional vector in the X and I have to learn a 2-dimensional function. It's a high dimensional space. Okay. Well, sound is even much more complex than images because in the sound I have to somehow encode it in numbers, right? While the images are already encoded, the sound I have to encode it. It's not my expertise anymore, so I will not explain you that. Physicists can explain that, but they featurize the sound and then they work in this featurized space. That's something that we need to do for sound, or also for words, or whatever. And we do it also in physics. But for us, if I'm simulating atomistic space, these are my data. Simulations, the space that I'm simulating. But if I'm in the 2D XY model, my data are different configurations of the 2D XY model. Many of them, right? And my space would be of high dimension, would be something that reflects the position of these arrows in all the box that I'm considering, right? And this would be my space. You can imagine that if you go to a 3D XY model where L is 100, you go to 100 by 100 by 100 dimensional space. Your data, it's really high dimensional. So from that, what we try to do is apply our methods. So we need to featurize our data, and then we can apply the learning. Okay? It can be even more difficult for those of chemists. You can try to imagine how to encode this for a computer, right? It's a graph, some things in the vertexes. But if I have to add the 3-dimensional of my molecule, it becomes a bit more complex. But if my molecule is moving in the space, it's even more complex because how to featurize that and how to obtain enough data to be able to work in these huge dimensional spaces, it's a challenge for all the other projects. Okay? One thing, let's start Another concept that I want to tell you is that in machine learning, we almost always, at least in supervised learning, we always do this kind of classification: train, validation, and test data. And it's important because we usually, when we learn data, we learn from our data, we need to test. We need to test our models. We need to test that what we have learned is meaningful. So since we unfortunately cannot always produce new data, what we do is, okay, I have all this amount of data, I will take a bit, the more important part for learning, and then take other parts for what is called tests that allow me to set what are called the hyperparameters of my method, because I would need to tune my method in order to better reproduce the data. And tuning that implies that you learn in the train space, and you learn many times. Imagine that you have to set, for instance, the number of coefficients of the linear regression that you are considering, the polynomial regression that you are considering. What you do is to learn with power 2, with power 3, power 4, power 5, and check what happens with my function when I try to predict in data that I didn't test it before. Okay. And this is the test set. The validation set would be what you use when you want to compare different models. Okay. If I try a linear regression, a neural network that we will see later, a random forest that we will see later, I want to see which of them is better for my problem. Since I already used the test set for setting the hyperparameters, I need some unbiased way of estimating which method is better. And that's done with the validation. Okay. This is, sorry, I explained it really fast, but I hope it's clear. So, tell me.
I heard many times that they talk about overtraining. If it's too large, the space of training, something like that.
Well, yes, not as far as you maintain a test and a validation set, no. What you can do is overfitting. We will see that later.
Okay, it's not the same.
It's not the same.
Okay.
Okay. So it's a right now. Okay. Imagine that I have this task. My task would be separate between blue and orange points, right? My function, my model, would be to find the line that separates both data points, right? I can imagine, make the hypothesis that this function is a line, or hyperplane if you want to go to higher than this. And this means that the hypothesis space that I'm considering is low, right? Because the complexity of possible separations between data points that I can have, it's also low. I can say, okay, it's a general line. I can also parameterize that. But then the complexity would be really high, right? Okay, let me try to go faster. You have time. Okay. The idea is that this complexity is extremely related with something that is called overfitting, and also with the bias variance thing. Bias variance, let me explain it really fast. Variance implies that you spread a lot. When you have high variance, you spread a lot. Bias is that your target is wrong. Okay. So your ideally, you want to have a low bias, low variance. But we will see that in the methods of machine learning, you have to arrive to a trade-off. You have to arrive to a compromise between a bit of bias and a bit of variance. Imagine that you have these data points, These are all of them sample format, let's say, to the power 2 function with sum of noise. Okay? There are 3 trained data sets. If I try to fit these 3 data sets with lines, you would see that these lines are almost the same. It means that I have a low variance, right? My predictions would be whatever my learning set is, my predictions would be almost the same. But my prediction is always wrong. Okay, I have a high bias. In this case, it's the opposite. In this case, what I do is to fit each data set with a really high powered polynomial. Okay? And what happens is that, okay, in average, you see that my predictions are kind of good, right? And in average would be good, but I would have a high variance. Each of the different models that I did for the different data sets would give me really different, right? This is what happens when I'm overfitting. Okay, I'm letting my model passing through all my data points, but then I also fitting the noise. So you have to arrive to a point in which of the complexity of your model, it's the one that you want, no more, no less. This is the one in which you minimize what is called the generalization error, because we are using supervised machine learning for trying to predict for something. It's not that we want to have the most fancy function that fits our data. We want to use it for predict something. We want to try to minimize what is called this generalization error, and this generalization error is minimal at the point where you arrive to the perfect bias variance trade-off. So we can arrive to that. Let's say if you see in this case, it's the same. I can fit my function with a line, right? A cubic polynomial, and power 9 polynomial. These are data from science. Okay? If I fit with a cubic, I'm okay. I think you will agree. So the problem, one thing that will give us an alert that we are doing overfitting is that when we go to the test data set, our error increases a lot because we are trying to do this kind of huge errors. And this is done. Imagine that, how can it be prevented? If in an ideal world, when I can get more data will prevent me to overfitting. Because, well, all of you have done some kind of regression. You see that when you go with a lot of numbers in your regression, then you can somehow fit it properly. Okay? One observation is that when you go to a higher polynomial, you see that the coefficients start to be really, really big. Okay? So one thing that you can do is try to control this coefficient, this weight in the case of general machine learning models. And what you do is to put a penalization in the loss. This is what is called regularization. This penalization can be in quadratic, that is what is called ridge regression, but you can also use order 1, just taking the absolute value, led to another kind of regularization, it's called Lasso. You can think about different things. Okay? And when you do that, just with a small regularization parameter, you obtain something that is much more coherent. Okay? So you don't have these big jumps in your function. Now, we finally arrive to the interesting part in which we start talking about real world algorithms. Okay. And the first one that I want to show you is this paper that is from 2020, where they used an algorithm that is called tree forest to classify particles from Alice experiment. Okay? And they are, I think here they are identifying kaons. Yeah? And you can see it, I don't know if it's clear, but at some point, the algorithm overperform your human classification. Okay, so okay, my idea when putting this is okay. I don't know anything about random forest. Imagine that I am expert in Alice. I would like to understand what a random forest. So let me explain you what's that. We need to know what's a decision tree. That's something that we do all the days, right? I mean, if you have program with if algorithms, nested if algorithms, give you that. The idea in tree algorithms is that these trees, decision trees, are learned from the data instead of programmed by ourselves. Okay? And what you do is to check how much entropy you lose when you try to classify. And that's what you want. Of course, the more the entropy, the lower the purity in your classification, right? This audience know what's the entropy, so I don't need to explain it. So you know that in pure systems have a lower entropy than mixed. It's the same here. What I want is purity in the leaves of my tree, right? In order to have obtain a good classification. So what you do is try to learn each time that you perform a branch, how good is your branching according with how much entropy you use, the information gain. Okay. This has problems, and the problem is that each time that you do this, you have to go to overfitting, you arrive to a pure classification. And the other problem that you have is that if you have a feature that is extremely important, it will dominate. It would not be so important if you make errors in the other things, right? So in order to solve this what people propose was the random forest. And the idea is, one thing is what is called bootstrap. I don't know if you know what's bootstrap. Your data, you generate several realizations of your data just by taking some of them at random, allowing repetition. Okay? For each of them, for each of these subsets, what you do then is saying, okay, I'm going to do the tree, but instead of doing just one tree for all of them, I will do many trees by choosing randomly the features. In this way, what I do is minimize the importance of these overweighted features. Okay, and you do it. It's just a matter of it's two nested loops. Okay, where you choose randomly first the features, then the data. Sorry, the opposite. First the data, then the. Okay, and then once you have done that, you put together all the results for your trees and take votes, because you are classifying. No? So you take the majority rule for classifying. Okay? Or you can take a probability according to what are, depends on what you want. Okay? Another case that I really want to arrive is to neural networks. Okay? And one of the things that you can use neural networks for, and there are some experts here that could explain it better than me, is to parameterize potential. Imagine that what we do in molecular dynamics, in classical molecular dynamics, is to parameterize. We don't want to do quantum computations each time, right? So what we do is parameterize the interaction between our atoms. The problem is that at this point, what we are doing is imposing the form of the potential. One can do with neural networks, with supervised learning, is try to learn from data the form of the potential. And for doing that, what you do is to use neural networks. Neural networks are probably the most successful machine learning algorithm nowadays. So it's important you have it in mind. And the idea is that we call it them neural networks because the idea is really similar to a neuron. This is a real neuron. You have the dendrites and nucleus and some terminal. In neural networks, what we have is in the dendrites, the input. Then in the nucleus, we perform some kind of transformation of our data. We put all of them together with a linear transformation, and then we apply a nonlinear function. And this is what gave us the output. Okay? For a single neuron, that's kind of easy to understand. It's just what is called the perception ansatz. What I do is to make the ansatz that what separates my data is this function. Okay? Where this f is a nonlinear function. And then I try to optimize these parameters, these weights, according with this loss function. Okay? That is the error in the classification in this case. So what I can do it here, can do it just with this data. I say that my function that decides if one thing is orange or blue is given by this. And then I want to say, okay, orange would be -1, blue +1. And try to apply that. This is my loss. What happens? What I need to do is to perform steepest descent. Okay. Steepest descent, it's a minimization algorithm. You go from your data, you know the gradient, and you can go to the minimum, right? So when I go with steepest descent algorithms, what I do is imagine I start from here. Sorry, I need to go to the. My algorithm, just by steepest descent, trying to minimize the loss, goes really fast to one solution, and then numerically, I arrive to a kind of really, really flat region. But since it's a bit long and we are short on time, let me explain you the end. We are still in the flat region at a moment in which I arrive to a good classification. This is something that I had done, I mean, in 5 minutes coding. It's really easy to code. So you can think that this idea, that it's easy, can be easily extended to nonlinear functions, because the problem that I had done before is my line, it's a line. What can I do? Imagine that instead of taking just this, what I take is that this takes the output of one previous layer of neurons. Okay? And that's why we call them neurons, because our brain works like that, also in layers. Okay? And we can go to deep neural networks just by adding many layers. Okay? This accumulation of linear transformation plus nonlinear transformation, I go ahead, linear, nonlinear, can be shown that can interpolate any mathematical function. You can put whatever function you want in this architecture. Okay? It's an universal approximation of any function. The problem is that, of course, it implies a lot of parameters. What I do is, first of all, I need a way to optimize these parameters. What it's done, it's backpropagation. It means that by using the chain rules, I can always correlate the derivative of the weight here with the weight here, and so on so far. So this is why it's called backpropagation, because when you perform a prediction using a neural network, you go in this sense. When you try to optimize, you take the output from here and start computing the derivatives from the previous layers. Okay. In potentials, we have specialized architectures for this. The one that I have shown you before is what is called a fully connected network. But in potentials, what we have is that we encode the environments of each atom in this way. And then we can kind of sum the energies. Okay. I'm almost done. Let me show you this one, and I think we will not have time for the last. But this one is one work that we did with Marcelo Almonte here. And what we used is what is a technique of unsupervised machine learning for identifying phase transitions. Okay, and this technique is called intrinsic dimension. Intrinsic dimension relies in one thing, in the concept of manifold. Okay, what I'm going to show you are always points in three-dimensional space. This is a set of points in 3 dimensions, right? But also here, I have a set of points in 3 dimensions, even they look in 2, right? Also here, I have points in 3 dimensions, even they lie in a 2-dimensional manifold. And I can make it more and more complex. All these are manifolds in 2D, but in an embedding space of 3D. So you would say that the intrinsic dimension of all these data points is 2. Okay? This concept allows us to correlate with the data. Okay, imagine that you have your data in 2 dimensions. This is a correlated data. There is no manifold there, just 2D. If you go to here, you see some correlation, you're still in 2D. If you increase a lot the correlation, your data is almost 1-dimensional, right? So, and that's where the physics came from. Because at the end, the correlations that appear in physics are translated to the data that you compute, your computer, and analyzing this in order to find these correlations allows us to detect physical properties just from the data. This is the good part, that by using unsupervised machine learning techniques, I can be absolutely ignorant in physics. And I can detect the efficiencies. Okay. So, how can I estimate the intrinsic dimension? Imagine that you have your data in this 2D. Okay, with me that this is 2D. If I based on this, the number of neighbors of a given data point is proportional to a quantity that is the density times the radius to the square, in this case. So if I start to increasing the number of neighbors with radius, I can see that this is a parabola, right? In this case, if I start doing exactly the same, I see that the number of neighbors is nearly aligned. Okay. So what you can do is think, okay, let's do it in practice. I can fit this with a log plot and obtain the slope as my intrinsic dimension. But this is a problem. It has a problem. It's that this is only true at constant density. And if we have priority distribution functions that are not constant, we can have problems. So we try to disentangle both methods, and what we use is the 2NN method. And the idea is that we focus on the ratio between the distance to the second nearest neighbor divided by the distance from the first. I will not show you why, that you can show that this follows a Pareto distribution that you can find with maximum likelihood of whatever approach that you want. And the trick is that you are assuming that the density within the second nearest neighbor is constant. So when you perform this division, they cancel. This is the idea under the method. And in practice, it works because in 2D, let's say that the condition that the density is constant within the second nearest neighbor is much lower, much softer than the one that assuming that the density is constant.
The example that you showed before, the one that in which you have, I don't know, is something that looks like this is like linear.
Yeah.
But the first two nearest neighbors are actually.
Yes. We will arrive to that.
Okay.
We will arrive to that. Because it's this thing. Okay. This is a property of data. Maybe it's a scale dependent parameter. You can, if you look really near, even if you look at the really near, it would be dimension 0, right? Because your point would be just single points. And this is the characteristic that allows us to define the phase transition. Why? Well, let me explain how I interpret it from the point of view of an atomistic person. In other things, I mean, we made some kind of mathematical derivation, but my interpretation was really easy. Imagine that you have a solid state. These are 9 atoms in a solid state, right? And I have several configurations. This one, this one, this one. Ideally, if I compute it properly, the idea in this space for all these configurations would be something that is proportional to the normal modes thermally accessible from my simulation. Now I have the liquid state. Okay, in the liquid state, I have these configurations, and ideally, my idea would be the total number of degrees of freedom minus 6 if I want to be precise. That if we have a real liquid, would be the total 3 times the total number of particles. But what happens in the transition? The transition I have almost all my system in the solid state and some particles that start behaving like liquid. What happens is that these few coordinates will be dominant when you try to distinguish between configurations. So you would have something that is mean. Okay. Indeed, if I'm not wrong, sorry to say that to physicists, I think it should arrive to 1. Because at the end, in the phase transition, you have just one parameter, but the other parameter can determine the configuration. Okay, I think it's too late, right? Let's stop it here, because otherwise, or as you say, if I can go to this one, or we can finish. Let's go. Okay. Well, the last one, I promise you, is this another paper that we did with Layo, and it's on proteins. And what we do is to analyze a really long simulation from Anton computer, that we were talking before, in which you have the protein that moves within several metastable states. And the question is that in the simulation, unless you start looking at the simulation and pointing, this looks like a different metastable state, you cannot do that. But we talk about milliseconds simulation, something that it would take you hours, and you would need a really good eye to look one of them to see which configuration they belong to, right? So what you try to do is cluster. It's try to find if there are groups in your dynamics. There are configurations that belong to the same group. And that's what you do. This is one easy thing where your data points are Gaussian distributed with several Gaussians. You can understand your data as a mix of Gaussian. And this is something really easy to classify. All classical methods work. But there is no rule that your data saying that your data in the space that you choose must be Gaussian. No. So your data can be something like that, or even something extremely not Gaussian, right? So in order to recognize the groups in this kind of systems, what we do is what is called density peak clustering. And what we do is trying to identify clusters as peaks in the underlying density field. Okay? We aim to identify these basins. And I call it basins because originally we thought in the free energy space. Because there is a mirror between the probability distribution function and the free energy space. Take the minus logarithm, right? So what we do is trying to find a way from the distances to obtain this. And from the distances between configurations, because we cannot work in a 3 million particles that we had in the, we need to reduce or work in a wiser way. And in order to avoid the reduction of dimensionality, we work with distances. We compare how similar or how far near are our configurations between them. Okay? And the idea is that your first thing that you can do is computing the density. You can compute the local density for computing how many neighbors you have for each data point, right? Within you define a radius in order to make it local, and you can do that. These numbers correspond to the order in density. Okay? The point one is the denser point, so the second denser point. Then what you can do is, for each data point, compute the distance from all the points that have a density that is higher than itself, and then take the minimum. This is taking the minimum distance from a point with higher density. And this is the key of the, you see that, for instance, for 0.8 would be 0.1 or 0.6, I don't know. For 0.10, it would be 0.9. This is the key for the algorithm, because the definition of a maximum in the density, it's a point that has high density, and it's relatively far from other points that have higher density. So what I can do is to plot this delta as a function of the density. And what happens is that the outliers on this graph are identified as cluster peaks, cluster centers, or density. Okay, then you assign all the other points like if you were doing a steepest descent algorithm. You are going to the nearest neighbor with higher density. Tell me.
But you have to define what an outlier is.
Yes, in the graph. No, in this case, you see the graph. You look at the graph. Okay. Let's see that. Let me tell you, this is the basics that I want to explain it to you. At the end, we had in the paper that I told you, we use an algorithm that do it automatically. But it's much more complex, and it was not the purpose of the plot. Okay. So in this case, it's not even an algorithm. I mean, we just compute the density that we can use if you want a Gaussian kernel instead of counting whatever method for computing the density. And then you compute this delta. Then you make what we tell the decision graph, and we, in this decision graph, identify the outliers. From there, you just have one parameter, that is the one that you use for computing the density, and it should be able to identify the peaks. Let me finish it here. Thank you. If you have questions, anyway, you are welcome.
Alex, yeah, we'll be over, so maybe you can keep questions. People want to leave it fine.
Yes, feel free.
Okay. No. One thing about this, I mean, this density for in general, everything to the distance that
Yes.
you are, I mean, you are using a metric.
Yes,
And this is, of course, if you change metric,
you change your result. You are biasing somehow.
Are there ideas of how to kind of go back to the
Well, the thing that, let's say, when you use Euclidean distance, as far as you are in a, you are kind of trying to be as aseptic, as agnostic as possible.
when you, I mean, for a simulation, maybe it makes sense, but if you do, I don't know, features.
Yeah, then there are ways of doing, there are ways of defining distances that are kind of classic, for, let's say, in machine learning, you define, I have this kind of method, this kind of features, I should use this distance. That's the agnostic way of doing that. Then, of course, if you are an expert and you know what you are looking for, you chop your space, because all these methods at the end work better if your dimension is lower. I mean, for instance, in the case of proteins, if I was looking for configurations, I'm not taking into account, at least not here, the water configurations, because I don't care about them. All the waters, I not even take into account the side chains, just taking the alpha carbons, because it's much easier to work with that. Ideally, in a world where I have infinite data and infinite computer power, I could use all of them. But it's not the case. More questions? Yes.
So in the density peak clustering, when the data is like in a way that the peak in the density, so you have some like layer events.
Mm-hmm.
The peak in there is the cluster, but the density is very low.
Yes.
Can you also
Well, in this case, what it's giving you depends on the noise, the amount of noise that you have. Because if you have a lot of noise, you will not be able to distinguish between your peak with really low density and a noise event, right? Because they would have high density, a lower density, and they would be far from the other things. You would not be able to distinguish between that. If there is no noise, then you just cut like that. Okay. Let me say, in order to be 100% honest, we usually don't have such a nice decision graph. We have a little noise, we have to decide. So that's what we work in an automatic way of doing that. In many cases, it works. I don't know if there are more questions.
I was wondering whether there is, if you have a long molecular dynamics, let's say ab initio molecular dynamics, and you want to learn the potential.
It would be really nice to have a really long definition. Yeah, well,
yeah, you have some ab initio molecular, and you want to learn the potential from
a neural network. It's the one that we showed.
Are there ways to speed up the learning from?
Well, the learning it's not so. It's not slow. What the problem is to obtain a big enough, a long enough trajectory, a long enough, a big enough data set to learn in such a way that you cover at least all the possibilities that interest you. The problem is that you are learning. When you go outside your learning, the generalization usually good, but you cannot do miracles. And when you are trying to learn for a simulation, you want to be to the chemistry. At least you cannot have big errors in your forces. So you cannot go really far from the things that you learn. So the problem, the main problem in learning potentials from ab initio is to have the data. Because at the end we are restricted to data from quantum calculations, but at the end they are expensive. Questions?
There are no more questions. Maybe we can thank